So as we begin lesson 5 from chapter 3, I wanted to do just a quick review of what we did in class yesterday, that money logic problem, where we were reasoning indirectly. If you recall, we had 3 envelopes, 2 ones, 1 $5 bill, and then I put a $1 bill in 2 envelopes and one in a 5 in one of them, and I kept one. Then we challenged students to determine what each person had in their envelope. We did this indirectly, and here's how we did that. We thought the teacher had the $5 bill. How do you start when you're going to reason indirectly? You got to get this terminology down. You suppose the opposite of what you're trying to prove. So if you're trying to prove that the teacher has the 5, let's suppose the teacher doesn't have the 5. And now we continue directly using the idea of syllogism. So if we say the teacher doesn't have the 5, then we start with that. If the teacher doesn't have the 5, then B has it, since I know I have the 1. See the if-then? We go on. There you see it, if-then. If B had the 5, then he would know what the teacher and I have. So see how we took B from the first, okay? This contradicts the fact that B doesn't know. He would know, he'd have said it, it would have been done. So we ran into a contradiction. So we always continue, it ends this way every time. Therefore, what we supposed, teacher doesn't have it, is false. We ran into a contradiction. And therefore, then the teacher has the $5, which is what we were trying to prove. So that was an indirect proof, and we figured that thing out using indirect reasoning. Here's another one. More money. Reminder here, now I'm giving you some already accepted facts. Throughout the rest of the year, we're going to call those the givens, things that we know to be true, the Legos we already have in our set. And in this case, the givens are this. One of the following envelopes has a true statement on it, and one of the envelopes has a false statement on it. Where is the money? So we know that to be true. So now we have to look at these 2 envelopes and see if we can figure out where the money is. I think you should pause this now and give this a try. And you're back. So where's the money? So let's try this. Let's reason indirectly. Let's say I think it's in envelope number 1. If it's in envelope number 1, that says in this envelope there is money, and in the other envelope there is not. So if that's true, then the money's in there, and then the other envelope doesn't have it. But now we go down to the other envelope. In one of these envelopes there is money, and in the other of these envelopes there is not. That's a contradiction, isn't it? Contradiction to our given, which, if you recall, said one of the envelopes is true, has a true statement, and one of them has a false statement. So if the money is, if we think envelope 1 is right, and there I gave it away, didn't I? We have a contradiction. So let's suppose it's in number 2. In one of these envelopes there is money, and in one of these envelopes there is not. If that's the true statement, then we go up to the other one. In this envelope there is money, and in the other envelope there is not, and that statement is clearly false then. So we've used the idea of indirect proof to solve. It works in many cases. It's a really good approach. Direct is easier, but sometimes you need to use an indirect proof. So we're kind of wrapping up our idea of what geometry is here. And here's an interesting cartoon. So Wiley's looking up the word ecology in the dictionary. Maybe today it would be on a computer, laptop, or a phone. And he reads, ecology is the cycle of life. Well, he doesn't understand the word cycle, so he looks it up. To move in a circle. Okay, well, he doesn't understand the word circle either. So he looks that up. It says to end up where you began. Well, so he looks up back at the beginning, and he's back at ecology because he's back where he began. Not totally humorous, but it does make a good point. You have to start with some things that you actually know before you can actually go anywhere. You can't define everything. You got to start somewhere. Geometry is a deductive system. So back to the idea of Legos. Geometry has its own Legos. Can you tell me what some of them are? Pause it. Try a few. Here are some. We have some definitions. We've defined some words. Some words we haven't. We've just used them because if you don't have some place to start, you can't build. We have some theorems. Today we introduce the fourth type of Lego in geometry. It's called a postulate. Postulate, the definition that we're going to use. See if this is a good definition. The definition of postulate, we're going to say a statement that is accepted without proof. It's a statement that's out there and we haven't done anything to prove that it's true. We're just accepting it without proof. Is that a good definition? So in your head you ought to be saying, well, what's the converse of that? A statement that is accepted without proof. If it is a statement that is accepted with proof, then it is a postulate. And that's true. So that is a good definition. So with our Legos, what are some of the geometry Legos we have? We have undefined terms, which we use in some postulates sometimes. These two I've got on the bottom because we haven't defined them, we haven't proven them, but we have to start with something and we end up in that circle. And we have some definitions that we also use in our work. We take all of those and we create theorems out of them. And then we use all four of those bottom type of blocks, undefined terms, postulates, definitions, theorems, to prove more theorems. And that's how we end up with our system of geometry. Looking at it a slightly different way, components of geometry, we have definitions like collinear, coplanar, non-collinear. We have some undefined terms. We have point, line, plane, and so on. We have some postulates that we're going to look at today. They're statements accepted as true without proof. And then finally we have theorems, statements proven either indirectly, we practiced that yesterday, or directly by using undefined terms, definitions, and postulates. And I should probably add logic as well. Notice well, there's some symmetry there. We've got definitions up here on the top. And then we have undefined terms. These are both words, groups of words. Postulate is a statement. A theorem is a statement. These we accept. These we've proven. These we accept. These we've proven or defined. So there's like a good compare and contrast question that might come up. How are these two alike? How are they different? How are these two alike? How are they different? How are definitions like theorems? How are postulates like undefined terms? So one more way to look at geometry as a deductive system, we can start with undefined terms. We need to. We can use those to define other words. We have to accept certain statements, certain postulates without proof. And there are three of them mentioned. We'll be looking at those as the year goes on. The ruler postulate, the area postulate, the side angle side postulate. We could take all three of those and we end up creating some theorems like Heron's theorem, or one that you probably know, the Pythagorean theorem. All of those together end up giving us geometry. So with a little drum roll, here is our first postulate. 2 points determine a line. We're just going to accept the fact that 2 points determine a line. Well, what does determine mean? We're not going to go in a circle here, but we do have to know what that means. I like to think of it as to define exactly one. In other words, if I have these 2 points, there is exactly one line that can go through those two. Now, I can see some of you saying, well, you know what? There's a little bit of space on the side here, and there's a little bit of space on the side there. So I could do another line through those two, and then I'd have 2 lines. Yep, but think about what a point is. Okay, so actually there's a point there. If you go on the outside of this, you're choosing another point there and another point there, and you have exactly one line through those. So there's our first postulate. Our assignment will be working with that. 2 points determine a line. We used that 117 times this year in our problem sets. Here's postulate 2. 3 non-collinear points determine a plane. You may recall I mentioned that. We talked about that a little bit in class this year. Again, determine means to define exactly one. So 3 non-collinear points, like those, determine exactly one plane. You couldn't put any other flat surface there and include all 3 of those points. There's exactly one plane. Now, something I like to point out, when this author uses postulates or definitions, he doesn't waste words. You need every word in this definition. So first of all, why would the points need to be non-collinear? Well, let's suppose they're not. Ooh, that sounds like an indirect proof. Suppose they're not collinear. Suppose they're collinear. See what problem might come up? Oh, look at there. Those 3 points are in that vertical plane, and those 3 points are in that horizontal plane. And if you extend your thinking just a little bit, there are an unlimited number of planes going through there. Angle each one of those just a little bit and keep going around. You can get an unlimited number of planes if the points are collinear. I'm thinking of like a book, the binding in the book. Think about all those pages that go through basically the same spot if you extend them just a little. So here we are with Chapter 2, Lesson 5. We've got some questions here, and we'll walk through those a little bit. So this is interesting. The dictionary tries to define point. We just accept it. Here's the definition. A dimensionless geometric object having no property but location. Think about that a bit. It's something that all it has is a spot where it is. Not a thickness, not a width, not a circumference. No dimensions, dimensionless, just has a location. So now they've got some questions for you to think about. Remember, dimensionless. All it has is location. So there are going to be 3 couple of sentences there. And then there's another definition. It says the only property is location. Now we go to the dictionary like Wiley. Location is defined as a site or situation. Site is defined as the place or setting of an event. Place is defined as a definite location. Oh boy. So we started there, we ended there. What happens when you try to define everything? You are not old enough for this. Maybe you've heard about it. Rin Tin Tin. Probably never watched it. Rin Tin Tin was a famous dog. Kind of like Lassie, but he ended up being more like a detective. He would solve problems. He would always be there to help out little kids that got in trouble. So here's a dialogue from a scene in a classroom in the Laurel and Hardy film Pardon Us. So the teacher asks, what is a comet? The student, a star with a tail on it? Yeah, that sounds pretty good. Maybe. Can anyone give us an example? And Laurel says, Rin Tin Tin. Rin Tin Tin, the dog. Which words in the other student's answer did Laurel misunderstand? So the student said this. Which word do you think Laurel had mixed up? And then why did he actually say rin tin tin? Hopefully I gave you enough for that. Again, we're focusing on some words here. If a weight is hung on the end of a piece of string, you got that pictured? The string hangs along a vertical line, a line that goes through the center of the earth due to, of course, gravity. From whatever point you suspend the weight with the string will have exactly one position. What postulate from today's lesson is illustrated by that? So you have your fingers hanging onto the string and there's a rock on the other end of it. Why does the string in this position make a better model of a line than when the string is lying on the floor? Think about that a bit. I like this quote from Bertrand Russell. I had been told that Euclid proved things, and I was much disappointed that he started with postulates, that he just accepted some things. Russell wanted everything to be proven. At first, I refused to accept them unless my brother could offer me some reason for doing so, but he said, if you don't accept them, we cannot go on. You can't prove anything if you don't have tools to start with. So here's some questions about this idea of postulate. Hopefully you're pausing when you need to. Would you have this table in your living room? Maybe some of you hunters, maybe not. Ladies, how about you? This is a duck pond table. 3 dipping ducks, like they're feeding off of the bottom, support a glass tabletop that represents the surface of the water. You know, I'm thinking, I don't know if I'd want to be looking at duck butts the whole time, but, you know, it's kind of a clever table. We're going to use this table. We've got this glass flat surface. We got the beaks down here on the ground, and then we got the tails up here supporting the table. So now some questions. Which postulate is this? And work your way through these questions about that table. And a few more about that table, but they introduce this idea. The points at which the duck's tails touch the table are coplanar because, and he's using the definition. How do I know? If. Points are coplanar if and only if there is a plane that contains all of them. So he says the duck's tails are coplanar. And some questions about that statement. Here you have to take a look at and try to visualize 2 intersecting cubes. Can you visualize those up there? He made one yellow and one blue. Sometimes it's kind of hard to see them. Hopefully you can get that. So now tell whether each of the following statements is true or false. So you're looking at it, B, C, and F, collinear. Is that true? B, C, F. Is that collinear? Well, it looks like it. It's on one of the edges of the cube. So you work your way through these, trying to determine if each one is true or false. I think one of these I might have something drawn in here. What is this? Which one is that for? E and G. Oh, I see what I did. Here they are. So maybe you can figure out which problem that's supposed to help you with. Okay, moving on. Japanese weights. I don't know how to say these, but I do know what's given in this paragraph up here. So a picul is a unit of weight that's 16 kwan. So a picul is pretty big compared to a kwan. You need 16 of those to equal a picul. Then if you keep going, a kwan, they say, is equal to 100 taels. Again, a kwan must be larger than a tael because it takes 100 of those to equal a kwan. And then a tael, the one we just did, is equal to 10 momi. I'm sure that's not how you say it. But again, a tail must be larger than a momi because it takes 10 of them. Again, hopefully you're noticing it's really important to look through givens and directions. Think them through before you try to solve any questions. So now there are 4 of them here. And then there are a couple of more on the next slide. Here's a dictionary definition. A pike hull derives from an expression for the load that can be carried by one man. Do you like that definition? A pike hull, the load that can be carried by one man. 2 questions about that. We're moving on to the financial world. These are statements that are on an agreement for getting a credit card. Hopefully you don't have your own credit cards. Most of you aren't old enough. Credit cards can be helpful. They can be a big problem if you don't understand that a credit card doesn't give you any money. A credit card lets you spend money you don't have with the promise that you're going to pay it back. And if you don't pay it back or you're late, they charge you extra, more than you spent. So they're necessary evil. Be careful. So here are the statements, and before you even try the problems, you need to read them through and see what you see. So the first one, a transaction finance charge is a charge made if a new advance is added to your account. Okay. Number 2, if you go over your credit limit, you will be charged a fee. Does that look like a type of statement we've been using this chapter? If you go over your credit limit, then you will be charged a fee. Number 3, a super check is a check designed for use with your credit card account. Well, number 3, I don't see the if and the then. Looks a little different. Number 4, if you are charged a fee, the fee will be added to your balance. That looks more like a conditional statement we've had. Number 5, if your card is lost or stolen, you agree to report it immediately. So those 5 statements, you need to look them through, answer some questions about them. All right, obtuse Ollie. He's a little obtuse. Doesn't always catch on. So he doesn't use a ruler. He had 2 points A and B here, and he drew that figure and said, aha, 2 lines intersect at 2 points. There they are. There's 2 points, and I got 2 lines through them. Acute Alice is a little sharper. Says that his description contradicts one of our postulates. So which postulate? What does that postulate say? And is she correct in saying there's a contradiction? Well, he doesn't give up. Why would it be incorrect to criticize Ollie's drawing by saying that our definition of a line says that a line is straight? What would be wrong with criticizing and saying, well, our definition of a line says that a line has to be straight? And then finally, obtuse Ollie's drawing and the criticism of it suggest a specific theorem. They don't ask which one, but they ask what is a theorem, to set it off from a postulate that we've done in this chapter. Here's the particular theorem. 2 lines cannot intersect in more than 1 point. That's a theorem we're thinking about. Apparently it's been proven. Study the outline of the following indirect proof, you notice that, of the theorem, and write the missing statements. Well, if we're trying to prove that 2 lines cannot intersect in more than 1 point, how do we need to start in our indirect proof down here? If you're drawing a blank, you can look ahead to the next one. If they intersect in more than 1 point, then 2 points do not determine a line. What does this contradict? Something that we are aware of, that we've learned. Therefore, our assumption, this line up here, is false, and what conclusion must follow? Well, hopefully it's what you were trying to prove in this theorem up here. Finally, set 3 is a little activity to try to help you come up with some clever idea here. You know that 2 points determine a line. How many lines could 20 points determine? The figure on the next slide shows 20 points arranged in a circle and all of the lines determined by them. Although it would be a challenge to try to count them from the figure, you may be able to guess the correct number by sneaking up on the problem. And his next questions here help you sneak up on the problem. Here's the picture referenced in that earlier slide. Boy, that'd be hard to count all of them. I mean, if I start here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 maybe? Maybe. How many points are there, by the way? Start right on the top there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, we knew that from the previous slide, Prof. 20 points. So those are the questions on set 3. See if you can figure out some kind of a pattern that might help you figure out how many lines 20 points would determine. So that's it for this assignment.